Welcome back. In this video, we would consider the Laurent series. Earlier, we have looked at the Taylor series. We have also looked at the relationship the Taylor series bears with the generalized Cauchy integral formula. This time around, it's time for us to take it a step further into the concept of the Laurent series. Remember that the Laurent series can be thought of as the extension of the Taylor series into the negative side. We would also consider what names we call them in a bit. Now, in this video, we would state the Laurent series as well as provide the proof or the derivation of the Laurent series. Now, let's get to it. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos. Let's begin. Suppose f of z is analytic in the region R1 less than z minus z naught in absolute value less than R2, and let C be a positively oriented simple closed curve around z naught in this region. Then for z naught in C in this region, f of z is equal to the summation j star from 0 to infinity aj z minus z naught j plus summation j star from 1 to infinity bj divided by z minus z naught j, where aj is defined by that integral from j 0 to infinity, and then bj defined by that same integral, but this time around for j from 1 to infinity. Now, this is the statement of the Laurent series. Now, you would notice that the biggest addition or the extension of the Laurent series from the Taylor series just exists within the stem. There are names we call this part of the series, and there's also a name we call this part of this Laurent series. We would get into those namings in a bit. But for now, let us first and foremost create a derivation process for this question. So let's begin. The very first thing we want to look at is, first, you realize that we say that for z not in C in this region. Why exactly is this important? Because we realize that because of the existence of this new formed part of the series, we see that z will have some singularities or discontinuities, what we would refer to as poles. In our next video or in a later video, we would consider the concept of poles and singularities in detail. But for now, just know that what we call singularities or discontinuities in this case are points to which, when you set them into the function, they make the function undefined. That's the blankest definition we will provide right now. Now, because of that, it means we want to evaluate and see the expansion of this function in series form within that region where such singularities exist. So how exactly would we create? Now realize that based off this process, one of the most important things that we can talk about is that we could, of course, refine R1 to simply be 0, and then refine R2 to simply be infinity, and then we would be left with the same bounds of the Taylor series. However, when we have R1 and R2, it means we could extend also R1 towards minus infinity and R2 towards infinity to take the entirety of the series. So that exactly holds true. Now, the next pointer you should also know is that in the case of the Laurent series, we usually only covered the parts where the arbitrary point S that we picked was greater than the variable in question. Hence, we could split 1 over s minus z within that light. However, for the Laurent series, because there would exist the negative side, we would consider the parts where s would be greater than z as normal, and then the parts where z would then be greater than s. These two parts would allow us create two functionalities within the series. And of course, those two functionalities would definitely affect how the formation of the integral will go. We'll look at this in much detail as we proceed. So let's first and foremost put our preliminaries in order. We'll start first and foremost by defining some curves and some bounds within this region R1 and R2. So let's R1 and R2, small R1 and R2, be such that R1 is less than R1, which is less or equal to the absolute value of z minus z naught, which is less or equal to R2, which is strictly less than R2. Right? So this creates a new region close to this set of values. And then we would also have that the point Z, of course, and the curve C will be included within the region that we just constructed. Now, we will try to showcase a representation, a diagrammatic representation or a geometric representation of what we mean shortly. Now, based off this new radius or new radii R1 and R2 that we have constructed, we can also construct regions or circles or curves around them. So we'd say also, let C1 be a circle centered or on Z such that rho is included in this region. Now, what is rho? Rho is simply a middle placed region that would lie between the first radius R1 and the second radius R2. The geometric representation will showcase what this is more and more, right? Then we can say that f of s divided by s minus z, in this case, would be an analytic function of s that would be, of course, analytic on the region bounded by C1. Now, this is on the C1 part. We can also further put more premise on C1 as C1 being the circle such that we have absolute value of z being equal to R1, which means that the largest distance within that circle is R1, which of course you can see is the lower radius here. Similarly, we can do same for C2, which will now be for the upper region, right? So we can say that this would imply that for a circle C2, absolute value of z would be R2 in this case. So we have C1 for the lower circle and then C2 representing the upper circle. Now, what exactly does this mean? Let us create a simple representation. It's not going to be, of course, very, very neat, but it gives us a good representation of what happens. Now, we have first and foremost our universal lower region, right? We would just do a simple representation of that universal lower region. Let's have this. And then here would have absolute value of z is less than capital letter R1. This will be the lower region. Now, on this, we have small letter R1, which extends inwards. And then we can have that as this. And this would, of course, be C1. This is C1 such that absolute value of z in this case is equal to R1. We have that representation for C1. Now, beyond C1, we will now have C. This is where we will now have C. Now, C will now be the region that bounds, of C will now be the curve, the simple closed curve, that bounds rho. Right? And then on C, which is the region that bounds rho, we will now have the upper radius, which we can draw like this. This will now be C2. And on C2, we can of course see that here we have that absolute value of z would be equal to R2 within the space covered by C2. So you can see that the region C, or the curve C, which includes rho, is within or in the middle of C1, which is the lower radius, which is the curve bound by the lower radius, and then C2, which is the curve bound by the upper radius. And then on top of all of this, you have the arbitrary upper region, where you have absolute value of z is equal to R2, which is the top. So this shows the representation we have. Where Laurent series applies is now on this inward region, which is on C, right? So bounded below by the curve C1 and bounded above by the curve C2. There we go. So what happens within this region, or within the circle or closed curve C, which of course includes the region rho, is what Laurent series wants to evaluate on. Now, if we have this representation, some very, very major things come into play. The very first thing is, how do we write equations or integrals on these regions? How do we do that? We remind ourselves of the Cauchy's second integral theorem. We remember that by the second integral theorem, that's the Cauchy's second integral theorem, which we just term the Cauchy's integral formula, we have that f of z would be equal to 1 over 2 pi I integral. Now, because our region of concern here is rho, which is of course bounded by the circle C, integral over rho f of s divided by s minus z ds. This is what we have. So now we have this as the integral theorem, which means that we can use this integral as a representation of what happens on this region. So how exactly can we do that? Let's look at that next. From here, we see that if we cross multiply with 2 pi I, we would have that 2 pi I f of z will be equal to the integral over rho f of s divided by s minus z ds. This is what we're going to have. Now, if this is our representation, it means that we can also see that, remember, if you look at the representation of the geometry, we see that the region bounded by rho is bounded below by the circle C1 and above by circle C2, right? And of course, rho is included in both of the regions, right? Because of course, it is centered on Z, right? So it extends from the center here towards the outside. So rho is contained within those regions or included in those regions, as already stated here. Now, if that's the case, it means that we can see that the integral over rho of f of s divided by s minus z ds is in fact equal to the integral on the top region, which is C2, f of s divided by s minus z ds, minus the integral over the lower region, which is bounded by C1, f of s over s minus z ds. And this makes a lot of sense, because if we are saying that we want to evaluate on this positively oriented simple closed curve in the middle, then it means to entirely get what's happening here, we would subtract the upper region. We will take the subtraction of the lower region from the upper region, which means if the lower region was taken from the center to this point and the upper region was taken from the center to this point, then subtracting those two would leave just the region from here to here, which is of course where our concern is. So that exactly works for this case. Now, do not forget that based off this representation, we already know that the integral over rho is 2 pi I f of z, right? So we hold on to that. We can have that written as 2 pi I f of z would then be equal to the integral over C2 f of s divided by s minus z ds minus integral over C1 f of s divided by s minus z ds. So now the question is, what happens in C2 and what happens in C1? Now, if we start first with C2, which is the first integral, for the points in C2, we realize first and foremost that based off those points, absolute value of z minus z naught will definitely be less than absolute value of s minus z naught. Why? Because z is less than s, because s refers to the points on the upper curve, right? So the points on the upper curve will definitely be larger than whatever point is below it, which are the z points, right? So z is less than x, which means the absolute value of z minus z naught is less than absolute value of s minus z naught. This is the very first information necessary. Now, if we use this, it means that just as we did it for the Taylor series part, remember the same split we used in the Taylor series, we'll have this as 1 divided by s minus z naught minus z minus z naught. Same way we did the split in that regard. And then we want to make this part 1. So we have 1 divided by s minus z naught into 1 divided by 1 minus z naught divided by s minus z naught. As always, remember, as I said in the Taylor series case, and I'll repeat it here, the goal is to always make sure that the denominator remains positive. So since s is greater than z, this representation is what ensures that there is a positive denominator. This, of course, reduces by summation into summation j starting from 0 to infinity of z minus z naught divided by s minus z naught, all raised to the power of j, right? And we have this representation in this case. Of course, we could return this into the integral, and we'll have summation j starting from 0 to infinity z minus z naught raised to the power of j divided by s minus z naught raised to the power of j plus 1. So it means that based off this, if we write integral of c2 f of s divided by s minus z ds, because 1 over s minus z is equal to this, it means that we would have this to simply be summation j starting from 0 to infinity integral over c, right, over the region inside f of s divided by s minus z naught j plus 1, and then ds, all of this multiplied, of course, by z minus z naught raised to the power of j. So this is what we are going to have now, because obviously z minus z naught has no part to do with the integral, so it can come out. So this is the first representation that we have. The next representation is what happens in C1. This time around, we're talking about the representation on the middle region. Now, if we are on the lower region, now if we are in the lower region, we see that in this case, for any point we pick on C1, it's going to be lesser than Z, right? It's going to be lesser than Z because this Z would be on the circle or the closed curve C in this case. So S is going to be less than Z. So if that's the case, it means that we are going to be saying that S minus Z naught will be less than Z minus Z naught in this case. This is what we are going to have. So if we use that narrative, 1 divided by S minus Z will be the same thing as, because there is a negation in this case, you remember the first split would have been S minus Z naught minus Z minus Z naught. But because S minus Z naught is less than Z minus Z naught, this split would give us a negative denominator, which we do not want. So what will we do? We factorize out minus 1 from the denominator. So we now have minus 1 divided by Z minus Z naught minus S minus Z naught. So therefore, the denominator now becomes positive, just like we want. Then we make this term 1, so we factorize out minus 1 divided by Z minus Z naught into 1 divided by 1 minus S minus Z naught divided by Z minus Z naught. And then this is what we have. Now, if we utilize this, it means we can rewrite this as minus 1 over Z minus Z naught summation j starting from 0 to infinity as well, S minus Z naught divided by Z minus Z naught power of j. That's going to be the sum to infinity. But do not forget that based off this representation, we would have minus summation j starting from 0 to infinity s minus z naught raised to the power of j divided by z minus z naught raised to the power of j plus 1. This is what we're going to have. However, because remember the terms are in the denominator position, in this case, we want to shift the counter away such that, because we remember that on the positive side where we have z minus z naught or the numerator side, we are already starting the counter from j equal to 0, which means in this case where we have z minus z naught in the denominator, if we also start the counter from j equal to 0, there will be a clash in both of them because they would not match. So instead, what we do is we shift the notation. Now, there is a simple trick towards shifting notations that I will talk about right now. When you add to the counter, you subtract from the variable in the term. And then when you subtract from the counter, you add to the variable in the term. So in this case, I want to add to the counter because I want this to start from 1. So if I want j equal to 1, that is I have to add 1 to this. Then I'll subtract 1 from the variable in the counter. So this will be j minus 1, and this will be j plus 1 minus 1. That's the easiest way to shift. So in here, I'm going to have minus summation j start from 1 to infinity s minus z naught raised to the power of j minus 1 divided by z minus z naught raised to the power of j. So I've easily shifted without too much complications. This would immediately mean that the integral over c1 of, and do not forget, you have f of s divided by s minus z ds would now simply be minus summation this time from 1 to infinity integral over c f of s divided by, of course, the representation here. But remember that I want to write this based off the entirety of this process. So I'm going to have this as f of s divided by z minus z naught j, right, s minus z naught j minus 1 ds, right? And I can have it like this. But then this is looking too rough. First and foremost, I want to take z minus z naught out of the integral because I can. The integral is in terms of s. And then I want this to come down. So if I want to do all of that together, I'm going to have minus summation j start from 1 to infinity integral over c f of s divided by s minus z naught minus j plus 1 by law of indices, because by the time I put it in the reciprocal, it becomes minus j minus times minus 1, which is minus j plus 1. And then this is ds. And then outside, I can now have z minus z naught raised to the power of minus j, if I wish. And this is going to be my representation. So I have a representation for the integral over c2, and I have a representation for the integral over c1. So I can now put these two together to get what my result for f of z would be. And that would, of course, be the full form of this question. Now, to proceed to that, I will now come back to proceed to that, we will now have that, remember, 2 pi I f of z would be equal to integral over c2 f of s divided by s minus z ds minus integral over c1 f of s over s minus z ds. Now, remember, there's a minus outside here, and then the integral itself came with a minus, so we'll put that all together. That would mean that 2 pi I integral over 2 pi I f of z would be, first and foremost, summation j start from 0 to infinity integral over c f of s divided by s minus z naught j plus 1 ds z minus z naught j plus, because you have minus here and then you have another minus here, so those will definitely cancel out. So you have plus summation j start from 1 to infinity integral over c f of s divided by s minus z naught minus j plus 1, right, ds. and then you have z minus z naught minus j. That's what we have. Now, this, of course, are very, very interesting concepts to keep in mind. Now, based off these two parameters, what do we immediately notice? We notice first and foremost that based off this, we would have immediately that we can rewrite this as 2 pi I f of z is equal to, this of course is a coefficient, this is of course another coefficient. So we can have that as summation, this start from 0 to infinity, aj z minus z naught j, and then plus summation j start from 1 to infinity bj z minus z naught minus j, right? And if you apply law of indices back on it, our summation j start from 0 to infinity aj z minus z naught j plus summation j start from 1 to infinity bj divided by z minus z naught j, where of course, as we quoted earlier, aj is equal to, now this is not full, so I should take this off here. So I would want us to have divided by 2 pi I on both sides, so that aj will be equal to 1 divided by 2 pi I integral over c f of s divided by s minus z naught j plus 1 ds, and based off the counter of the summation from 0 to infinity, that means j starts from 0, 1, 2, and goes. And then bj would be 1 divided by 2 pi I integral over c of f of s divided by s minus z naught minus j plus 1 ds. And of course, based off the counter from 1 to infinity, j will start from 1 and go. So there we have it, and that finishes our derivation of the Laurent series. It's important to note, as I said, that this part where the z function is the denominator, we usually refer to this part of the Laurent series as the analytic part of the Laurent series, the analytic part, which is usually also the Taylor series part as well. And then you have summation j start from 1 to infinity bj divided by z minus z naught j. This is referred to as the principal part. The principal part. So you have the Laurent series as the sum of the analytic part as well as of the principal part. This is very, very important, because you realize that based off the region of operation and based off the radius that you would be operating within in questions, not all of those regions will have both the analytic part and the principal part. Some will just have only the analytic part, some will just have only the principal part, as the case is. Your job is to always figure out which of those parts will exist, or if both of them will exist for any kind of question we have. Now that we have looked at this derivation, remember, if you were to compare this to where we started off, we already have the integral, right? aj and bj, just as the integral is written, so we have derived it correctly. So now that we have looked at this derivation, and we have of course extended the relationship it shares with the Taylor series, we've said the analytic part just represents the parts of the Taylor series we have, because the Taylor series talks about the region, the positive part of the region, right? While the Laurent series covers both the positive and the negative part of the region, which we refer to as the analytic and the principal part of the region. Now, this is very, very important, as the case is. It's also important to note that we could also combine the Laurent series into one single formula, right? In that case, we could rewrite the Laurent series as f of z is equal to summation j start from minus infinity to infinity pj z minus z naught of j. So you notice the counter now starts from minus infinity to infinity, which means it now contains the principal part. Remember, because the variable z is in the denominator, it means that by the time it comes to the denominator, it becomes a negative. So when you say j is 1, 2, 3, you have -1, -2, -3, -4, which is the negative side. So here, of course, you now have that Cj would of course be equal to 1 divided by 2 pi I integral over C f of s divided by s minus z naught j plus 1 ds, and then j will start from 0 plus or minus 1 plus or minus 2 and so on and so forth. So this shows a shrunk conversion of the Laurent series. Now, the Laurent series is very, very important, and that is why we have spent so much time in deriving the Laurent series, because number one, it shares the premise for the study of residue. As we will notice when we get to that part of the series, you would see that the residue, when we talk about calculus of residue, the residue itself is simply a term in the principal part that you generate from the Laurent series. And this, the reason why we consider residue itself is because for some functions, it might not be so easy for you to generate their Laurent series so as to find their residue. But then you should also know that the residue is usually the coefficient of the first term in the principal part. We would also shed more light on that later on. So all in all, this video has showcased the derivation of the Laurent series. I hope you've been able to follow through. If there are any points where you got confused, you can play back and watch the video again, or send me a message in the comments for clarity wherever possible. As always, make sure to like, share, and subscribe, and turn on your notifications so you do not miss any of our videos.